All right, so it's time for us to get to 9.2 today. So we got 9.1. And please make sure you're reviewing the videos and clicking review for me. That would be much appreciated. So let's go ahead and get into our next one. So let me get you here. All right, so here we go. Let's get this thing started. Let's get it started. All right, 9.2, which is we're going to be talking about multi-staging experiments. I won't do too much of the modeling games, but we're going to, what's it take to have multiple steps of the experiment, independent events, and conditional probability. Okay, so first of all, let's talk about tree diagrams. Here we have a spinner with 3 different colors. Okay, so suppose the spinner is spun twice. That makes it a multiple event. We got 2 events, 2 spins. Okay, the tree diagram shows how the possible outcomes are. So if you go through here, I begin with 1 spin. The first spin, I'm either going to get let's see here, let's try this again. Okay, we're either going to get a blue on the first spin, a red on the first spin, or a yellow. Then we spin it 1 more time. So if we got a blue, we could get another blue, so we get blue, blue. We get a red on the second one, so I get a blue, red, and so forth. And you see how it goes. Each time I spin, I've got a 1 in 3 shot. So if you come down here and we look at all the possible outcomes, what we're talking about. These are all your possible outcomes. Okay? So how many different possible outcomes do we have? Okay? So we're going to have these possible outcomes. So the probability of any individual outcome of a blue, blue, a blue, red, okay? Now notice this is my sample space. We talked about that last time. A sample space has the sets here, brackets, and this is blue, 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 red, and so forth. Probability of each outcome is 1 out of 9. Notice they're all different because of their order. Okay? Now, that's tree diagram. Here's your sample space version. And then we can also write this as a chart. One spin, second spin. Okay? Blue, blue, and so forth. And you can get the same 9 versions by using it as a table. They have some good tables in your book too. Run through those tables. They are going to be helpful. So, when rolling a pair of fair dice, now when we talk about fair dice, we're talking about a 6-sided die, okay? 6 different numbers. Find the probability of event A equaling double 6s. So that means we got to roll 2 die. Okay, that's the pair. And so we need a 6 and a 6. Okay? So we go through that. So we can do a chart with that. And so we have the first die and the second die. So we can roll a 1 and a 1, a 1 and then a 2, a 1 and a 3, and so forth. And we have 36 different possibilities. Okay, this is also a chart that might help you, I believe, on some homework. It is in your book. Okay? There is only one way to get double 6s. It's down here. So you're going to have a probability of 1 out of 36 to get the double 6s. Okay? Now, how else can you get it? Well, what's the probability of 1/6 would be 1/6. Okay? So we can also go that route with it algebraically, which I'm probably getting ahead of myself. That's 1/6 for the first 6, 1/6 for the second 6. So what can I do to get to the 1/36? You multiply them. All right. Find the probability of rolling a sum of 7 or 11 when a fair dice. Well, here's your 36 again. I need a sum of 7, adding up to 7, and adding up to 11. Okay, so we got that. So where can I get 7s? Well, there's a 7, a 5 and a 2, a 3 and a 4, right? Here's another one. Here's another one. So there are 6 of them. What about an 11? Well, here's an 11, and here's an 11. Okay? Are there any other 11s? Did I miss another 11? No, I don't see another 11. That's only 2. All right. So there are 6 here, 7s, 2 11s. Okay, so there's your sum of 7s. And they have a typo in here. That's supposed to be a 2. I was going to say, I looked at that, so there's not 6 ways to get an 11. There are 2 ways to get an 11. Okay, so that is, just make sure you understand that. Let's go into my red here. This is wrong. This is a 2. All right, so that's 2 out of 36. Okay, so if that's all together, you would get, if you add those up, you should get your sample space. All right, the sample space of the experiment is, so I have a new sample space. Why did that not get out of here? There we go. Sorry about that. Sample space for the experiment is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But the sample space is not uniform. The probabilities of the given sums are not equal. Okay, so we're talking about dealing with totals of the die still. Okay, so my sample space is a 1, a 3, and so forth. Okay, here's my 7, here's my 11. Okay, so notice they are all different amounts. Okay, some of them are repeated, but there's only certain ways to do things, so they're not all equal. Okay, so the probability of rolling the 7 and the 11, you add them up, probability of the 7 and the 11, okay, because they are not uniformed, I can add them and you're set. Okay, so we add them up, we get 8 out of 36, which would actually reduce to what? 2 out of 9 probability of one of those two. Okay, reduced form is always the best form. Okay, they didn't quite do that on this one. A fair die is rolled. Let E be the event of rolling a sum that is an even number and rolling a sum that's a prime number. Okay, so if we look at even and prime, okay, so we look at this list, okay, we are trying to find the evens, see where we're at here. All right, so the E and the F, so these are all your evens and your primes. So I had to figure out how they wrote this. I couldn't remember how they wrote this. I looked at it earlier. So there's my evens. These are my primes. Now also remember, this is a prime too. Okay, so we're going to find the probability of rolling a sum that is even or prime. Okay, so let's look at that. So we have that number. So even, prime, even, prime, even, prime, even, not prime. Okay, so we're going to pull these out, the probability of a 2, probability of the 4, the 6, the 8, the 10, the 12. Those are all your evens, and here's all your primes. Okay, so that's all of these. Those are all your probabilities. Now when you add them, the nice thing is all of them get added together so the bottom stays the same, and I get 32 out of 36, okay? Which also would have a reduction to that, which is, what's my reducing? This guy who never did this one didn't reduce. I can take a 4 out, that's going to be 8 out of 9. Actually, an 8 out of 9 probability. Okay. All right, now, different ways you can do that, okay? These are not mutually exclusive because the 2 is the same in both of them. So you can also find it by probability of the evens plus the probability of the odds minus the one repeat one. So that's the one we talked about last time. And then this other one is the contradiction one. Then you're better off, or the complement, excuse me, not contradiction, complement one. I wouldn't use this one. This one takes too much thought pattern. Okay. All right, more multi-states. So here you have an issue of 3 balls, 2 are white, 1 is black. Okay. So if you're drawing one at random, you got a 1/3 chance of getting this white ball, 1/3 chance of getting this white ball, and this one, 1/3 chance of getting the black. Okay. Now, that being said, though, wouldn't you have a 2/3 chance of getting a white and a 1/3 chance of getting a black? Okay. So suppose that ball is drawn at random in the box and figure, and its color is recorded. When the ball is then replaced, that's huge. The ball is replaced. Whoops, clicked the wrong thing. And a second ball is picked. The sample space of the 2-stage experiment may be recorded. You can go black, 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 white, white, black, white, white. Okay. Now, how does that tree diagram out? Well, if I have a 1/3 chance of black, 2/3 of white. And then on the second draw, I got another 1/3 try with the 2/3 white. Okay, so the outcome of black, black is going to be 1/3 times 1/3, which is 1/9. Of black, white would be 1/3, 2/3, which is 2/9. Same thing for a white and then a black. But then a white, white would be 2/3, 2/3, and multiply those together, you get 4/9. Okay, which should be the better probability of getting a white, white. Okay, because there's more whites in each pot. Okay. It says for all multi-stage events, the probability of the outcome along any path of the tree diagram is equal to the product of all the probabilities. And that's what we did right there. We multiply. Okay. Now, what if you're taking 1 by 1 without replacement? Okay. So you got to look at this. This is a little different. Okay. So if you remember, you have a black and then a white and a white. So if you take out the black, then you can never get another black one, because if you do not replace it without replacement, it's huge. That means when you take out the black first, it's only 2 whites left. Okay, which means you get a white, you get a 2 out of 2, because there's 2 left in there. If the first draw you make is a white, that's a 2/3 chance of getting that. Now you got a 50-50. There's only 2. You have a black. At this point, you have a black and a white left. So you either get the black or the white. So, excuse me, as you look at these, you multiply them this way. And you can get their probabilities using the tree diagram. That's what makes the tree diagram so effective. Okay. Independent events, when an outcome of one event has no influence on the outcome of a second event. Okay. Without replacement has an effect. If I put the white or the black ball back in, then it has no effect on it. Okay, a die has no effect on the next. Every time it's a 1/6. A coin is an independent. Never, always will be 1/2. Okay, if 2 coins are flipped and the event 1 is obtaining the head on the first coin, and event 2 is containing a tail on the second coin, then event 1 and event 2 are independent, because it's always going to be 1 out of 2. Okay, so in this independent, you're going to have a 1/2 to get a heads, and then it's still 1/2, 1/2 on the second coin flip. So when you multiply them out, you're going to have 1/4 all the way through. So it's going to be equal all the way through. For any independent events, you're finding the intersection of them, or basically, this is the big key right here. Whoops. Okay, for independent events, you just multiply probability of the first event times the probability of the second event. That's the biggest part of that. Okay? And they do give you some good examples in the e-text that you can run through. Okay? So this figure shows a box with 11 letters. Spells out the word probability. Some letters are repeated. Okay? Suppose 4 letters are drawn at random from the box, one by one, without replacement. Again, big time, without a replacement. What is the probability of the outcome baby with the letters chosen in exactly that order? All right, so a few things before we go further with that. Without replacement is always important, which means when you start with 11, the next draw is going to be 10, and so forth. Okay, and the other thing here is exactly in the order to spell the word baby. Okay, now, can I spell the word baby? Yes, because there are 2 B's, an A, and a Y. So I can spell the word baby. So it is possible. Okay, so we're only interested to find the word baby. So the probability of getting a B is 2 out of 11. Okay, because there's 11 letters. An A, there is only 1 A in there. There's 1 A over 10 left over. Why? Because we already took off one of the letters have been taken away. Now, if that first letter was a B, that means for the next B, I only have 1 B left over. Because remember, you have 11 total letters. There are 2 B's, 1 A, and 1 Y. That's what we had in there. So that's why the 2 out of 11, and then you subtract 1 from the total number of letters every time. 11, 10, 9, 8, so forth. Okay? Now, if I wanted to spell something else that had 2 A's in it, I wouldn't be able to do it because I only have 1 unless we do with replacement. Okay? So the probability of the first is 2 11ths because there are 2 B's and so forth. Okay? So I kind of discussed all of this already on why that works. Now, what do we do with those numbers? We multiply them through. Now, notice how big the probability is because you have to deal with it. Now, again, I don't know why the person that wrote this, they already had a misspelling in it, but wouldn't this reduce by 2? Okay, that'd be a, what, a 3, a 9, be 18, be 6, and a 0. So it's a 1 in 3,960 chance probability. Okay. All right. Now it says, consider 3 boxes shown. A letter is drawn from box 1 and is placed in box 2. Then a letter is drawn from box 2 and placed in box 3. Finally, a letter is drawn in box 3. What is the probability that the letter drawn from box 3 is a B? Okay, so we're going to take one letter, probability of being a B. It says call this E. So if you look here, the probability of the first draw is 2/3 for an A, 1/3 for a B. Okay. Then if you go back into the box again, okay, I'll go backwards again because we had 2, 3, right? So now this could either be an A, so this is either going to have 2 A's in it, or it's going to have 1 A and 2 B's, correct? So I have 2 A's and 1 B, or 1 A and 2 B's. Okay, depends on if this was a B. Correct? Now, if I'm either going to have when I bring one over here, if it's an A, there's two A's. So if I bring over the A now, so if I bring over an A, I'm either going to have two A's, three B's, or four B's and one A. Okay, so that's what I'd have left over there. So there we go. All right, so if you notice the last one, I'm either going to have two A's out of 5, three B's out of 5, or one A left over, if that's a B, and four B's, and so forth. And then to find your total possible outcome, you again multiply down the strands, and multiply here to get here. You multiply down here to get here. You multiply 1/3, 1/3, 2/5 to get here. Now, remember what the question was. The question was, what's the probability? What's the probability of being a B at the end? All right, so where's the B's? Here's a B. So here's a B. So I have a 12. It's all the ones in blue. Here's a B. Here's a B at the end. Remember, we're just looking for this B right here. A B at the end. And so we take all of those, and because they're mutually exclusive, I can add them all up. And I get a 31 out of 45, which is reduced. Now, the conditional probabilities, okay, if A and B are events in sample space, and they're conditional in the event that B occurs, given the event A has occurred already, which is something else has happened, you take the intersection of the probabilities of A and B and divide it by probabilities of just A. So, how does that work? What is the probability of rolling a 6 on a fair die if you know that the roll is an even number? Okay, so in this case, probability of the 6 is 1/6, and then if you know when you roll it's going to be an even, you divide it by 1/2 because there's an even number, a half of the numbers are even. So you do 1/6 divided by 1/2, which is not fun for somebody else. Okay? All right, so I hope that this is helpful. Again, go through your notes, go through this video, also go through your e-text, because the text will help you with a lot of your homework too. It gives you some good examples, especially those charts. Okay? All right, so I hope this helps.